Hey everybody, this is Mr. Ainsworth. Good morning, and we are going to get into practice on closure. How do you prove algebraically here that a set is closed under a particular operation? Okay, so we want to prove each algebraically. All right, so let's get right into it. You got to define your unknowns and knowns first, and you got to be really specific. Okay, so we need to, in this case, number one, we want to prove, all right, that all even integers are closed under multiplication. So we have to prove that an even integer times an even integer is still an even integer. Okay, so a couple basic things. All right, so let's take out our red pen. Okay, so in when it comes to even and odd, so even form, we talked about this in a previous lesson. Okay, even form. So for any number here, n is equal to, no, actually not n. Let me use a here. So an even number a, if it's even, it's in the form of 2k. Okay, where k is an integer. K is an integer. An integer. It's 2 times some number. Like 20 is 2 times 10, where 10 is an integer. 18 is 2 times 9, where 9 is an integer. Okay, that's even form. Okay, odd form. Okay, it's different. Okay, they look different. They behave differently. So odd form, let's say a different number here. We say that b is an odd number if it's in the form of 2 times an integer, all right, plus 1, okay, where k is an integer. Okay, for example, let's say 19, well, that's 2 times 9, which is 18 plus 1 more. Okay, so again, this is the integer right here, obviously. Okay, so if it's in this form, it's odd, 2k plus 1. If it's even, it's 2k. All right, so that's what we have to start off with. Okay, so here I want to take two even integers, two different even integers, and I want to multiply them together and show that it's even. Okay, so you say, okay, let a equal to 2k, all right, where k is an element of an integer, is an integer. Okay, and b, okay, is a different one. Okay, so b is equal to 2l, let's say. Okay, hang on for a second. Okay, so back to the lesson here. It's just interrupted there. Sorry about that. All right, so here we 2k, or 2 times an integer. K is an integer, L is an integer. So we have to make note of that. Okay, so k, okay, and L are integers. Are integers. So you could write it out in English like that, or you can use symbols and you could do this. Okay, they're integers. You can say they're element of z, where z is a set of integers. Okay, so remember integers, z, here the set of integers. Here we go. Here's a set, so -2, -1, 0, 1, 2, and forever. So it's that whole numbers and their opposites, okay? So you have to know what integers look like. If you don't know what they look like and visualize them, well, it's kind of hard to work with it, right? So you have to know your sets. You have to know your number sets. So K and L are integers, they're even, okay? Look at this even form. So you start off with even form. And so right now what we have to do is multiply them together and show that the result's even. All right, the application is multiplication. All right, so here's the proof here. So proof, you go A times B, right? A times B. So you take 2K, all right, times 2L. We have to take an even times an even and show it's even. All right, so what you do is that order doesn't, matter, right? The way you multiply doesn't matter. Even form is 2 times a number. So remember that back of the top here, 2k means 2 times an integer. So even form is that. So I have to show that this is 2 times some integer. So I'm just going to regroup them here. I'm going to say, okay, 2 here, the leading 2 is equal to k times 2 times L. So I'm just going to regroup, right? K times 2 times L right here. And I have to show that this is even. So what I do is I just regrouped right there, because in multiplication, the order and the grouping does not matter. You guys should know that from grade school. So is an integer k times 2 times L, which is another integer, is that an integer? Okay, is an integer times an integer times an integer an integer? Okay, and we said yes in the previous lesson. So previously, we knew that an integer times an integer is an integer. So this portion right here, okay, this is nothing more than an integer. And because of that, okay, we have 2 times some integer value, which means it has to be even. This is even form. And if it's even form, the result must be even. So A and B must be even. Okay, so an even, here's the thought process again. This is an even times an even integer, that is, times another even integer is an even integer. And that's why it is closed, okay, because the result is back in the set. Okay, that's what closure is all about it. Under a particular operation, if you multiply 2 even integers and you get an even integer, well, then it's closed. Okay, so the proof is we're complete. So I'm going to say QED, quod eris demonstratum, that which was to be demonstrated. That's Latin, okay? So there's your proof. You have to show that the result is even. So let's get some more experience here. Okay, so again, you state what you're starting with. Okay, you're starting off with 2 even integers. Okay, so you say let a equal to 2l or 2k, let's say, and b equal to 2, let's say 2l. They're both even. Okay, so they're even, and now we have to add them together and make sure that an even plus an even gives you another even. So we have to show that it results in even form. Okay, so let's do it. Let's add them together because now the addition or the operation is addition. So we say a plus b this time, not a times b, because we're adding now, okay? We're adding. So a plus b is equal to 2k plus 2l. And I have to show that that's even, which means I have to show that it is an even form, which is right above. It's 2 times some integer. So all I do is just distribute out the 2, okay? So k, 2 times k plus l. All right, distribute out the 2. That's the key thing here. Distribute out the 2. Let me highlight that. It's just an algebraic technique, okay? Look at that. The 2's in common, so distribute it out. And guess what? An integer plus an integer is another integer, so this is an integer here. And now we are in even form. So this is equal to 2 times an integer, which is even form. And because of that, an even plus an even, again, we started off with 2 even numbers here. So an even plus another even, all right, gives you an even. Therefore, it's closed. So remember, when the operation changes, you just go with the flow and perform it depending on the operation and make sure that the result is in the same form. That's what closure is all about. Okay, so now we're going to take 2 odd numbers here and show it's closed under multiplication. Okay, so here we go. Odd numbers are different. Okay, so get the evens out of your head. So we're going to say let A and B be odd. We're going to take 2 odds in here. So A is now an odd number. So it's 2k plus 1, okay, odd. And b is a different one, so 2l plus 1, odd. Okay, we're going to multiply them together and show it's odd. Okay, so here we go. Here's the proof. So a times b is equal to 2k plus 1. You got to multiply them together. 2k plus 1 times 2l plus 1. Okay, and now when you multiply binomials, you multiply using the either distributive or the FOIL method. Okay, so 2k times 2l is 4kl. 2 times 2 is 4. So here we go, multiplying. So 4kl, you're just multiplying. 2k times 1 is obviously 2k. And then you got to distribute down here. 1 times 2l is 2l. So plus 2l. Plus 1 times 1 is usually 1. Now we have to show this in the form. So odd form. Okay, just let me bring this back up to you, and let's go backwards here, is 2 times an integer plus 1. 2 times some integer plus 1. That's odd form. So what I'm going to do is I'm going to distribute a 2 out of here to make that 2 happen. So distribute out a 2. So let's do that out of the first 3 terms. So 2 times I know 2kl, it gives you the 4kl. 2 times k gives you the 2k, so plus k, and then 2 times L would obviously be 2L, and then there's that plus 1. And then the question is this stuff inside here, okay, is that an integer? So 2 times an integer, that's an integer. Plus another integer is an integer. Plus another integer is an integer. Okay, so this is definitely an integer. Okay, so we have the form of an odd. We have 2 times some integer plus 1. Okay, so that means that A times B must be odd. Okay, so therefore, oops, I'm at the bottom of the screen here. It's kind of hard to write. Um, Hang on for a second. Let me try to do this here. Well, anyways, it's an odd form. So A times B must be odd. We started off with an odd times an odd. All right, and we got an odd. Okay, so it must be closed. And that's the whole idea of it. You just got to get some practice here. Like in number 4, we have to prove that all numbers of the form 3n plus 1, where n is a natural number, this is supposed to be a natural number, okay, is closed under multiplication. That means we take a number like this, multiply it by another number in that form, we get a number in that form. Okay, so here we go. So let A, we start off by saying you got to pick 2 numbers, right? So let A equal to 3n plus 1. Oops, 3, excuse me. 3n plus 1. B equal to some different one, 3m plus 1. Those are the same forms. Okay, look at that. This is the form now. They're in the same form where n and m are integers. So n and m are integers. Okay, there we go. And then you start your proof. So here you go. You multiply them together and see what happens. So a times b is equal to 3n plus 1 times 3m plus 1. Again, you're multiplying them together, right? So you got to multiply. You got to multiply. And then use the FOIL method again, or distributive property. Okay, so here we go. Let's multiply them together. So 3n times 3m is 9nm. 3n times 1 is 3n. Again, you're seeing algebra 1 here, guys. This is an algebra 1 based proof. So 1 times 3m is 3m, and then 1 times 1 is 1, just like the previous problem. Now I have to show that it's in the form of 3 times an integer plus 1. This is 3 times an integer plus 1. That's the form. It says so. So what I need to do is factor out a 3 to make it look like this. So again, algebra 1. So factor out a 3. So 3 times 3nm gives you that 9nm, right? Distribute out the 3 from the 3n, you get n. Distribute out the 3 from the 3m, you get m. And then bring down the plus 1. You can check this, okay? Distribute back and you can see it. And so this is 3 times an integer plus 1. Okay, so this right here, that's the integer. If you multiply integers, you get integer. Add another integer, it's still an integer. Plus another integer, you get an integer. So this is in the same form. Same form as the set. Okay, and I'm talking about this right up here. Okay, so it's closed. So you multiply the number in the particular form. I took 2 different ones, A and B, multiply them together, and I get the same form, which means it has to be closed. Okay? All right, number 5, same idea. Let's do it. Let's take a perfect square now. This is misspelled, so fix that. So let's take the perfect squares of the integers. Okay, so what are they? Well, let me see. 1 squared is 1, 2 squared is 4, 3 squared is 9, 16, 25, dot, 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 dot. Okay, perfect squares. And multiply them together. A perfect square times a perfect square gives you a perfect square. All right, so you start off with 2 general ones. So let A equal to n squared and B equal to m squared. Okay, these are, some perfect squares. You got to start off with 2 different ones. So here again is the proof. So you're going to multiply them together and get a perfect square. So a square times a square gives you another square. So a times b is equal to n squared times m squared. And you have to show that it's a square. So it's some integer squared. That's your form. So is this some squared? So let's rewrite it. Let's write it as n times m quantity squared. These two things mean the same thing. So the question is that an integer? Well, is an integer times an integer an integer? And the answer is yes. We talked about that in every single previous problem. So this is an integer squared, which means it has to be a perfect square. Okay? So you take a square times another square, and you get another perfect square, and that's why it's closed. Okay, that's the idea. A square times a square gives you another square. Just like 4 times, let's say 25, those are perfect squares, gives you 100. Well, and that's, guess what? That's 10 squared. That's just an example, by the way. And that's how you handle it. So these algebraic proofs, you got to get used to them. And you get used to them by doing. Okay, so prove that D is of the form 2n, 2 to the power n, where n is a natural number, is closed under multiplication. So the form is 2 into an integer power. Okay, again, n here, look at the exponent here, or excuse me, not integer, natural. Okay, so it's to the, some natural number power. Okay, so n is some natural number. There's your form. So if we can show this, we're good. So we're going to take two different ones. Okay, so you say let, okay, a is equal to 2 to the nth power. B is equal to 2 to the, some different power, where n, okay, and m are natural numbers, so they're part of the natural set. And then you prove it. So a number, these two numbers, if we multiply them together, do you get a number in the form of 2 to some power? All right, so here we go. A times b is equal to 2 to the power n times 2 to the m power. Well, in algebra 1, when you multiply like bases, you add the exponents. So this is equal to 2 to the power of n plus m. Okay, add exponents. Going back to algebra 1, believe it or not. Okay, and guess what? N and m are naturals. So in the previous lesson, in previous activity, we said a natural plus a natural is a natural. Like 1 plus 4 is 5, and that's natural. 3 plus 8 is 11, that's natural. So this is in the form of 2 to some natural number, which happens to be the same form as back in the set. So this number here, whatever it may be, is still in the set, and that's why it's closed. Okay, so a times b must lie in the set. All right, and again, you could put down QED at the end of each one of these. All right, quad eris demonstratum, it's Latin. Research it, just type it in Google, QED, and you'll see that the Greeks, they used to put that at the end of every proof. Okay, now as anything, especially this kind of stuff, when it comes to learning something abstract, especially when it's pure algebraic, you have to go and re-listen to things. And so if you need to rewind that video, go for it and listen to it again until you get the hang of it. Okay, so use the videos that I post effectively here. These are just, some practice on how to prove things algebraically. All right, this is Mr. Ainsworth. I'll see you in my next lesson or in class, one of the two. Take care. Bye-bye.